In the last lesson, we looked at what we needed in order for a cloud to form. We talked about the cloud needing a solid surface. We talked about it needing to be at its saturation point. And we also talked about how it had to be that particle of air then, once it had reached its saturation point and had those condensation nuclei available, it had to be cooled down to its dew point. So now we're going to talk about how the cooling part occurs. We're going to talk about 3 different methods, or 3 different ways that air is cooled on Earth. Now, our first way is through convection. So convective cooling, once again, we talked about convection currents in the mantle, right? And I told you it was going to come back to us with convection in the air as well. And it's the same process where warm things rise and cool things sink. So we've got warmer air is going to rise, and cooler air is going to sink. Now, in air, though, that relates to air pressure. So when we have air that's warm and it wants to rise up, it's in an area of low pressure. There's not a lot of air pressure, is basically the air pushing down onto the surface of the planet. And so when we have an area where the air is rising, because it's warm, the molecules are lifting up and they're spreading further apart as they get higher up in the atmosphere. And so the pressure is really low. In areas where the air is really cold and the air is descending, and that makes it an area of high pressure. So at the poles, we have big masses of cold air because the air over the poles is really cold because the sunlight doesn't reach it directly. And so the air is descending and it's pushing down on the surface of the planet. And all those air molecules are getting crammed in closer together. And anytime you do that, they want to move away from there because they're getting all pushed together. And so the air is going to move from an area of high pressure to an area of low pressure. But the convective cooling happens because as the air rises, so like at the equator where the air's temperature is really warm at the surface, we have that air starting to rise up, and as it rises and gets further away from the surface of the planet, the molecules move further apart. If you take your hands and you rub them together, you can feel the heat building up between your hands as you rub them together. That's because your hands are close together. Now I want you to take your hands and I want you to put them about, 5 or 6 inches apart, and I want you to make that same motion like you're rubbing your hands together. Well, they're not touching one another, and so there's no heat being generated, right? Because there's no friction going on. The same thing happens with our air molecules. Our air molecules in areas of high pressure where they're being all squeezed closely together, they're rubbing together like your hands are, and they're generating heat. Where you have areas of low pressure, where the air is rising up and those molecules are drifting further away from one another, they can no longer rub up against one another, and so they cool off. So air that was once warm at the equator, as it goes further off the surface of Earth, starts to cool off. So there's 4 different ways that air can be lifted in order for that convection to occur. So these are all types of convective coolings. And there's orographic lifting that we'll talk about, frontal wedging, convergence, and localized convective lifting. So our first one is orographic lifting. The prefix here, oro, at the beginning, refers to mountains. And so orographic lifting is lifting that happens because of mountains. So the air gets pushed up the side of a mountain and it cools off because it's being forced further up off the surface of the planet. And usually that's happening because of local winds or global winds. So you could have air that's down at sea level that is much warmer, but as if it's near a mountain range, and as the air comes from the ocean and it pushes inland and pushes that air up the side of a mountain, it starts to cool off. And this is why we get a lot of rain in the Pacific Northwest, because this exact process is happening. The air is getting pushed off of the Pacific Ocean, it comes and it hits the mountain ranges like the Cascade Mountain Range, and then it gets pushed up the side of the mountains, and we get temperate rainforests, or areas that have really lush vegetation on the side of the mountain that's closest to the ocean. Now, the mountain, though, so the air gets pushed up the side, and it cools and condenses and rains and makes clouds, right? And it rains on the ocean side of it. But now, as it slides back down the other side, we end up with what's called the rain shadow effect. So because when the air gets pushed up here and it rains out, okay, remember the cold air gets colder, it can't hold as much moisture. So this nice warm air mass has come up off the ocean, it's gotten shoved up the side of the mountain, It's cooled, it's condensed, and the rain has come down. But now it's going to slide down this back side of the mountain, and it's going to heat up again as it goes down closer to the surface. And we'll talk about why that is in just a minute, because that's a different kind of cooling and heating. Um, but it does heat up as it goes back down. And remember, warm air can hold more moisture. So now you've got this air mass that can hold a lot more moisture, and it doesn't have a lot of moisture because it all rained out over here. And so we get a desert on this side. And that's what the rain shadow is. This area over here on the right-hand side is in the shadow of the mountain, and all the rain happens on the other side. So if we go back to my example about the Pacific Northwest, so we think about Oregon, if you've ever been there and you've been on the coast side of the Cascade Mountains, then what you see on that side is big tall trees, lots of grass, it's really green, things grow really well. But if you've ever been to eastern Oregon or eastern Washington, that's in the rain shadow of the Cascade Mountain Range. And so now we have shortgrass prairies, and we have a lot less vegetation. You don't have as many trees because they don't have as much water. The same thing happens with the Rocky Mountains. In the Rocky Mountains, particularly on the west side of the Rocky Mountains, you have lots of tall trees and all that kind of stuff. But as you come down off the Rockies and you go out past Denver, now you're into the prairies, and you're into the Great Prairie area that's in the center of our continent, which is in a big rain shadow of the Rocky Mountains. So another way that air can be lifted is through what's called frontal wedging. So the front is the boundary between a big area of warm air and a big area of cold air. A front is just one big area that has a common characteristic throughout of temperature and moisture. So when we have two of those meet, that's where we start to get some rain. So this is where a warm air has started to overtake a cold air mass, and because that warm air holds more moisture, it slides over the top because it wants to rise, and it cools off as it goes up, and so we get some rain. This is what's called a warm front, and it's the reason why when we have a warm front come through, we don't get big, massive thunderstorms and stuff like that, because it's just sliding up over the top of that cold air mass. But frontal wedging is another one of our ways that convective cooling happens. In convergence, I'll show you a picture of this one. Convergence is just where we have two air masses that strike one another and get moved up, and I'll show you a picture of that in a minute. And then localized convective lifting, we see here as dust devils, is one example of why localized convective lifting happens. So here we've got converging winds, and they get pushed up. These would be local converging winds, because our global wind belt doesn't allow for large areas of wind to do this, but this happens on a local level. If there's a storm coming from one side and a storm coming from the other side, it can push the air up like that. This is our localized convective lifting. In one area on the surface of the planet just gets heated up more than the areas around it, and it causes the air to rise. And that's why we get dust devils here, because one area started to heat up a little bit more, the air started to rise, it started to spin, picks up dust, and we get a dust devil. All right, so we had convective lifting. That was our first one, our first way the air is cooled. Our second way the air is cooled is through what's called an adiabatic temperature change. And this is happening just because there's expansion or compression of the air. So I'm going to go back to the rain shadow effect really quick, because this is another example of an adiabatic temperature change. So here, on this side, we have orographic lifting. Okay, the air got pushed up, and that's why it cooled off. But on this side, the mountain didn't shove it down. Okay, the air slid down the bottom of the mountain because it went from an area of high pressure to low pressure. Okay, and down here, as you get closer to the surface, the air gets compressed together. It's pushed down by the weight of gravity. It's pulled in by the center of the planet, which is where our center of gravity is, and the air starts to get compressed back together. So this side over here is an adiabatic temperature change. The air heats up because it's getting compressed down due to greater air pressure. So that was an adiabatic heating. Adiabatic cooling is happening as that convective lifting occurs. We have the expansion of the air that's happening, and the dew point changes as we get further up. And you'll see that the bottom of the cloud happens at the level where the air temperature has reached its dew point. So That's why the bottom of clouds tend to be kind of flat, is because usually the air temperature is pretty consistent in the upper atmosphere, and that's where the dew point has reached. Our third type of air cooling is advective cooling. And this one happens usually because we have an area that's an ocean or one of our bigger lakes. The wind comes over the top of it, it brings a mass of warm, moist air, and it comes over the land. And the ocean was warmer than the land is, and so as the air moves from that warm ocean over the top of the land, it cools down, it reaches its dew point, and it makes fog. So this is why we only get fog. So we only get fog here. It has to be a really cold morning that happened after a big rainstorm. So it rains a lot, there's a lot of moisture available, and then the cloud cover breaks, and so there's nothing there holding in all that heat at night, and then that's when we get fog here in the valley. Alright, so we're going to talk a little bit about cloud types. We're not going to go too crazy into this. When we talk about that, we've got three basic kinds of clouds. We've got our cirrus clouds, which are really high ones. There's different there's like subcategories underneath these, but these are the big three. So our cirrus clouds are our high wispy clouds, actually angel hair clouds. Our cumulus clouds look like the piles of cotton, the big puffy clouds. And then we've got our stratus clouds that look like thin layers or sheets. So in the summertime, we see lots of cumulus clouds, particularly around the time that we get the monsoon. The cirrus clouds tend to be fair weather clouds. So we see those when there's not a lot of moisture in the atmosphere. You're not going to get rain out of cirrus clouds. You're only going to get rain out of your cumulus and your stratus. In the winter time, when we get our winter storms, we get lots of stratus clouds, and particularly the nimbostratus clouds, the big, thick, heavy, dark ones where it feels like the ceiling is really low, where the clouds are kind of pushing down on us. So here's our cirrus. So this example in the picture are cirrocumulus. So they're still really high clouds, but they look like little puffs. Looks like you've taken cotton batting and kind of stretched it out across the sky. Our cirrostratus would be, we wouldn't have this little separation here. It would just be nice and thin and all the way across. Our altocumulus clouds. So alto means middle. If you are an alto in a choir, you sing, your voice is kind of in the middle. You're not too low in the bass and you're not too high in the soprano. Same thing with your middle clouds. The altos are in the middle. So we've got altocumulus, so these are lower than our cirrocumulus, but still puffy. So the example here is an altocumulus cloud. So middle level clouds that are still broken apart and puffy. Altostratus are going to be a middle level stratus cloud. So they're going to do the same thing as the cirrostratus. Still a nice sheet-like, not this little separation in here. Usually thin. And then we get our low-level clouds. So these are our sheet-like clouds, our stratocumulus. These are really cool, and these ones we generally see these when we get lots of rain. And if you look at the bottom of the clouds, they're really low. And you look at the bottom, and it's like the bottom of the cloud dips. When it talks about looking like a scalloped bottom, scalloped means that if it's scalloped, it means it kind of goes like this along the bottom. So it kind of looks like it's rolling across the bottom. This is an example here of a nimbostratus cloud, and that's where we get all of our rain from. That's where predominantly when we get winter rain, it comes from a nimbostratus cloud. And here's all of our clouds. We get one kind of cloud that kind of doesn't meet the bill for any of those, and it's a cloud of vertical development. And so this cloud right here is what is called a cumulonimbus. That's not what I wanted. Apparently my pen is disappearing on me, but it's a cumulonimbus cloud. So it has, this is where we get our big monsoons from in the wintertime and in the summertime actually, but mostly the summertime. So because there's so much heating that occurs and we get that big warm chunk of air, moist air that comes up from Mexico, that comes up from the Gulf, region and picks up from both the from Baja and from the Gulf of Mexico. The circulation sets up and the air movement sets up that we get this big chunk of moisture that comes up from Mexico, and then it's still really hot here, and so it causes a lot of vertical lifting. It causes a lot of air rising, and it rises really fast, and then we get our big thunderstorms.